Okay, what you see here is the interface of COMSOL multiphysics. We are about to solve a one space dimensional heat conduction problem as our first example. So if we look around here, there are three sections. This is the main flow of the solution procedure. Here are some details of this one, and here is the graphical output area. So we have to make some choices here. So we first say that we have a one-dimensional problem, and I proceed to the next choice. And you may have good choices here if you have done something before, but in general you have to specify this one for heat transfer in a solid. So I left click this one, and I add this to my selection of physics down here. I also see that my dependent variable with the temperature denoted by capital T. I proceed to the next choice, and here I have to specify stationary or a time-dependent simulation. I choose now stationary, and I press the finish flag here to indicate that I'm done with the initial choices. I got some new things here to consider. First of all, I can choose some units for describing geometry. I don't care too much about units right now, since I consider a pure mathematical problem. But we can imagine this as being a heat conduction problem. So what I do next now is to go to the Geometry tab and right-click this one. And I get the chance here to specify my interval, which is my domain. And here I specify which is the leftmost endpoint and the rightmost endpoint in this interval. And this is fine with me. Consider the interval 0 to 1. So I build this interval, and you see the geometry of my domain popping up here in the graphic window. I could now proceed to mesh this, and I do that down here. So I right click here, and I build a mesh with default size elements. With left clicking this, you see that I get here 15 elements. I could choose finer elements, of course, if I like, and also fewer. You also see that we got 31 nodes. You see that down here, but actually we see only 16 here. And this is because in each element you also have an interior node in the midpoint, because the default in COMSOL multiphysics is not to use piecewise linear variation on each element, but rather to use piecewise quadratic. We don't have to worry too much about that right now. So we have specified the geometry and the mesh, and we proceed to specify the physics. So we have already made the choice, heat transfer in a solid. So I left click this one, and it concerns this domain here that is already selected for us. The equation to be solved is this one. And now we have to specify some data here. For example, the heat conductivity K that we called lambda in our notes, and the heat production Q, and also the density rho and the heat capacity Cp. So the heat conduction K we specify here as a user-defined constant 1, and similarly with the density, which we will need for the time-dependent problem later, also to be 1. And similarly, the heat capacity to also be 1 for simplicity. Okay, fine. We also want to specify now U here has a default definition of 0. And that is fine, because that is exactly what we want. This term is not present in our case. We already had these two terms. But we have to specify Q. the heat source, and that is not part of the menu here. So I go up here and right click, and then you see that here I can specify a heat source. The first ones here is for adding data about the domain, and these ones with the dots is for adding more information about the boundary nodes. So I left click this one, and there is an equation here for a boundary condition, or rather for the heat production that we see here. First of all, I mark this domain here, and I add this to my selection. It's here. And I now specify a user-defined heat production intensity, which is constant 2. Now everything about the interior of the domain is specified. It's a geometry, the mesh, and also all the data of the differential equation. Now we want to proceed to specify also the boundary conditions, what happens at the endpoints. Over here we had a thermal isolation, and that is part of the default setting here that you see over here, thermal isolation. So the only thing that we have to do is to change the boundary condition over here to a temperature condition, a condition on the temperature. To do that, we have to add this possibility here by right-clicking again here and going down to the boundary information. And I have some information about the temperature at least part of the boundary, so I press this one. And where does this apply? Well, I mark this part of the boundary, the leftmost boundary point. I add this to my selection, and here is the type of boundary data, boundary condition that I now have. The temperature is T0, and here I can specify the desired value of T0, and in our case that was 0. So now all information is entered, and we can then go to solve this problem. So we go to study, I right click here, and I left click on compute, and then hopefully a solution should pop up in front of our eyes. So we see the graph of the solution over here, and if you look at this, it's actually the curve 2x minus x squared that describes the temperature. You see that at x equals 0, the temperature is 0. And you see that at x equals 1, the derivative is 0. That is, we have no heat flux over here. You also see that the curve bends up a little bit, which reflects then that we have production of heat inside this domain here. So this is as far as